Okay, so hello everybody. How many are? Five. Um, Similar to last lecture, we will be recording the lecture. It will be online on Ilias later this week or maybe later today, however the case. My name is Berzan Gashi. I am a postdoc at the Fraunhofer Institute for Applied Solid State Physics. I'm holding this second lecture now, and I think up from next week, Professor Kwai will be back. Today we will talk about power semiconductors. Last week we talked about antennas. That is also part in your, as I mentioned, the important thing to remember there is the antenna pattern, the polar plot, what the horizontal and vertical axes tell you, what are the main characteristics of an antenna, namely directivity, gain, aperture, and so forth. These are the things that may appear on the exam. The things that we investigate in CST are for you to have an introduction on how modern antenna design is done nowadays and where the path leads to antenna design in the RF world. Now, we talked a lot about antennas, and obviously for using those antennas in transmitting systems, you need some amplification of the signal beforehand. Where we said that especially in the modern antenna design, which is done in millimeter and the sub-millimeter wave range, the loss in energy is tremendous in free space, and the reachability of targets is very low, sometimes even 20 centimeters away, sometimes a few meters away, but in a very constrained operating conditions. Thus, the solution to that is to have a signal which is boosted beforehand, either have a large array or have a signal which is boosted beforehand by an amplifier. Thus, we will talk about power semiconductors, or what's the principle of power semiconductors principally used, or just a short introduction to that. And I think a more detailed explanation will be given by Professor Kwai in the succeeding lectures. Nowadays, power electronics finds mainly use in everywhere devices, from DC-DC to then also RF frequencies. In this case, we will talk about the RF application of them, mainly in what is directly affecting us, either in our phones or directly in the case of a base station. The base station obviously has a far more higher power capability. Otherwise, our phones would die in every 30 seconds if they had such a power amplifier in them. But we do have similar devices that are low powered in our phones that boost the signal that we transmit and also boost the received signal that is taken from the antennas. Mainly in the power stations you have nowadays, or until now, we had the 4G let's say protocol or transmission technology, where you would have certain quadrants of the transmission center, where it would cover certain areas of a three defined areas of wherever it is located, and you would shoot maximum power in these three different areas. Nowadays, what is being done with 5G is that multiple transmitters are being integrated into one power station, into one transmit station, not power station, and these are being used to target more refined areas, more refined chunks of a transmit area, and in these more refined chunks to transmit a controlled range of power. When moving to higher frequencies, obviously the absorption in free space becomes larger. Thus, the targets that are reached become more nearer to you, meaning that if you operate something that has a transmitter Wi-Fi at 2.4 gigahertz, you can reach far further away than operating something at 60 gigahertz. In order to circumvent this problem, you need electronics, or you need semiconductor technologies that are oriented towards high power outputs. Basically, what you use is both high voltage and high current gains, which means that the semiconductor technology has to evolve from what we see nowadays in our phones and into one that is capable in handling high electric fields, so that you can generate high output powers. We move also from technologies that have a low band gap to one which has a higher band gap. The higher band gaps enable a higher efficiency. They also enable a better mobility of the conductors, and have low ohmic contact resistances are implemented in the back end of line of the processing technologies. An issue is obviously also heating, and one main characteristic becomes the packaging of such elements, which can be both structured horizontally and vertically. What do I mean with structured horizontally and vertically? You know, for example, a HBT, for example, Ziga HBT, silicon germanium, which is an example of bringing together two semiconductor technologies in order to shift the band gap so that you have a large band gap material in order to produce technology that is capable of handling high electric fields. And these technologies, the heterojunction bipolar transistor, is a vertical device, so a device which is not structured laterally but which is structured vertically. And an HEMT device, for example, or a field effect transistor device is structured laterally. Both can be used for power generation. One uses it over the whole width of the base, whereas the other one is in terms of the gate length. The HBT is as a base and the other one as a gate. As I said, vertical and horizontal inclusion due to the higher doping, a higher mobility of the carriers, meaning that the Fmax and Ft are far higher than what is currently used in the semiconductor world in pure silicon. Higher higher band gap allows for higher output of voltage in this case, but there's a constraint between how large the band gap can be and what is the mobility of the carriers and how that affects then the output power versus the Fmax, which is the maximum current gain at the frequency where your current gain is unitary. So this is how usually like an example of a semiconductor for high power usage is. You have these bars. They're called usually power bars because there's just parallelized transistors. Parallelized transistors with a high gate width. Usually in this case, I think this is an example of a MHEMT transistor, or it can be also a GaN-HEMT transistor, which is parallelized. And these are then bonded towards the packaging. Why do you need a certain bondage to the packaging? Is because the input impedance is fairly low, and you need to then transform it via a LC network. Everything but the rest, which is highlighted, is the packaging part, which either consists of bond wires or metal insulator metal capacitors, and these leads that go to output lead and input lead. These output leads and input leads, what can be seen to the left or to the right, are just transmission lines that enable you to transfer your RF input into the transistor bars and to receive your RF output. On the side, you'll have then bias Ts on the inside gate. You will have a bias T, which then feeds your VGS, gate source voltage, and on the right you will have a drain bias T, which feeds your drain source voltage. The extrinsic shell of the transistor, you can see in the dark color is the gate. What is the drain and the source is what do we call as the extrinsic shell of the transistor. This is where the ohmic contacts are present to feed. This is where we try to feed the respective the respective transistor finger with this kind of a structure, and you just imagine this kind of a structure is what is seen then in the highlighted part where this says semiconductor, and these are then just parallelized, and over where the bond wires are is where, for example, the gate is. There's one bond wire goes to there, and then on the other side the drain goes the other bond wire, and the source is connected to neutral, to ground. A source is required. That's why I said on the gate side you will have a gate source voltage. On the drain side you will have a drain source voltage. And you have to always consider the parasitic capacitances that come up due to the existence of such feeding structures. So in order to contact the gate fingers, you'll have to have all these like feeding structures in order to be able to contact them, and each feeding structure introduces gate and drain capacitances that are undesired. Now, simply move to a technology, simply use a technology like this silicon technology is not possible. It's traditional silicon node. Why? Because they're mostly applicable for low power and for computing applications, such that are fast switches to shift bits. We don't want to do that. We'd rather want to have high frequency capable devices that have a large gate width such that we can produce a lot of output power. In order to be able to handle that, in order to be able to realize these high output powers, you need a device which is capable to control the electric field. And in order to control the electric field, these devices are doped. So a certain amount of polarized doping occurs, homogeneous doping across the structure, an extra amount of doping, so that the E fields are, so that the channel is able to handle the electric field. Furthermore, there is also a metallic coating on top of the gate, a metallic shielding, in order to even out the electric field across the drain and gate, across the drain gate connection. Here are some examples of how such a device can be. It can take a drain source voltage of up to 28 volts. That's because of the doping and because of the shielding on top of the gate, which prevents that the electric field pinches off somewhere, so that temperature develops and then burns through the device. That is avoided by doing a uniform doping and added uniform doping in the shielding on top of the gate drain contact. Through the parallelization of such devices, you can, these are such devices called the laterally diffused devices. Why laterally diffused? Because of the laterally diffused doping that is added. These devices are used for power generation up to 4 gigahertz, for very high power generation. And how is that achieved? Is by parallelizing them. As said in this example here, you can just imagine one such device and just parallelize. And all these parallelized devices then are bonded towards their microstrip line transmission. They're combined together, and then you get the power and output outside. So it's very, very simple. It's always the parallelization of these devices, of these gate fingers. So as I said, the respective lateral diffusion is achieved by adding a higher p-type doping across the substrate, increasing the p-type doping, and by adding this shielding to the gate drain contact, so that you can achieve a homogeneous E field spread across the drain gate contact. And the homogeneous E field allows for a higher voltage to be applied. As we said, 28 volts can be applied to such a device. That's completely different from what is applied to a Intel chip or a whatever Apple chip in our computers, as they're not oriented towards power. We had the example. We'll move on. The issue with these is that the input impedance and the output impedance are far off from what we would like to see in our. Usually, when you design an amplifier, when you design any system, you agree upon having a reference impedance, upon having certain impedance where the complete system functions. Because you're using multiple components from different vendors, there's a unanimity that mostly these components are either have a reference impedance where they are matched to. And in this case, the reference impedance that one would want to match to is 50 ohms. But you see that these kind of transistors have, due to the higher doping, have a very low input impedance, which then has to be transferred using a transformation matrix in the Smith chart. I don't know if you've seen a Smith chart beforehand. A Smith chart is basically just displaying the complex impedance points that could be targeted or could be reached by an operation of an amplifier, whether that is the input or the output characteristic. At the input and output, the reflection coefficients that can be seen, usually in the horizontal axis where the impedance is listed, and then on the upper field of the Smith chart is the inductivity part, and in the lower field of the Smith chart is the conductive part of the impedance. And when you move over the circles, you move over equi-resistance lines, which vary then in the imaginary part of the impedance. Whether it is more inductive or more capacitive. depending on what your device is. Usually our devices will all move along the capacitive portion, so on the lower field of the Smith chart. Another issue important for that is that we said we are applying a very high voltage. We're also trying to get a lot of power out of our high frequency devices, RF devices. The problem with getting a lot of power is that the efficiency is not always 100%. The efficiency for amplifiers ranges at the theoretical maximum of 70%. Usually for an AAB amplifier, class amplifier, then you move further to C class amplifiers and so forth. Your efficiency decreases depending on the input drive as well. So how much input power you drive into the device. That is why it is from all these things, when we apply a DC bias to enable the generation of the RF output, we have a lot of losses, and these losses are heat. What are the losses in an active device? They're heat, and this heat spreads all across the packaging. This is here. Can you see it? Here's the packaging of the device. This package is what we showed beforehand here. And this is basically how it usually is mounted in a PCB board, where then you have the packaging, and then you have the respective matching networks and the respective bias tees to feed this kind of circuit. Is the temperature distribution, and nowadays this temperature distribution is really also simulated in the same program that I showed you beforehand, CST. In the last subject, we used it to design antennas. The same program has heat solvers, which you can use to define a heat source and heat sink, and see where how the spread of from your heat source to your heat sink, how the spread of the temperature is evolving over the operation. This is basically tried to avoid it by considering how we package these devices. As I said, this packaging of these devices nowadays is not really, you don't really have a molding compound where you flip the chip and then you have a carrier, and then you put a mold on top of it. Usually these technologies that operate at these high output powers are, most of them don't even have a final passivation layer, which means that it is very difficult to even coat something on top of it, as it changes the complete behavior of the structures. So they don't have anything that after they process the complete back end of line, there's no encapsulation of the device. So in order to encapsulate the device, or in order to use the device, you have to think of other forms of packaging. That's why this particular form of packaging, usually you would think that a transistor is flipped, a transistor bar is flip chipped on a carrier, and then the molding compounds comes on top of it, and leads come out so that you contact it. That is not the case here. In this case, it is just glued on the carrier, and the carrier is some metal sheet or some metal confinement, which is in this case, you see that this structure here with this with this transmission line that come in and out of the packaging, and then you bond to it. And that is displayed in that's displayed here. And here we can then talk a little bit about the channel temperature. What is then taken as the channel temperature in this case? It is taken in order to generate the channel temperature, it is the global channel temperature. You take the thermal resistance, which is of the device, which is strongly dependent on the packaging. That's why the thermal resistance of this device, in order to reduce the heat in order to help the heat distribution, in order to help increase the heat distribution, is placed in a metallic packaging frame, which is supposed to carry out the heat, and that is then mounted on a PCB, which is also metallized to have a certain heat transfer. The formulation doesn't really come up in any of the, but this is an example how that is expected as the equivalent power that is radiated out, meaning that, or equivalent power that's delivered. In this case, it is the DC power so the power that is lost, or the power that aids into the heat, because the energy that is lost is basically heat, and the heat that is produced is from the DC power you put in, versus plus the input power that you drive into your amplifier, minus that power that you get out of the amplifier, the RF power that you take out. So given that your amplifier will have an efficiency of around 30 to 60, 70%, a lot of that DC power and input power is not the input power, but a lot of the DC power is lost simply into heat. And this heat transfer is based on how your packaging is designed, because the packaging then introduces the respective thermal resistances, the effective thermal resistance, and these thermal resistances are simply added up into the packaging. And you have the thermal resistance that is on chip, and the thermal resistance that is with respect to the PCB and the chassis and the setup. So the channel temperature of your device, of your power device, will not only depend on the device itself, but it will also depend on the respective packaging. You will have two branches of whether the device itself, the respective thermal resistances, and the thermal resistances of the packaging. That was a simple introduction. Let's move on with the lecture. Now, we did mention that we want to move and operate into devices that have a higher band gap. Why is that the case? Because a higher band gap allows us to apply a higher operating voltage, and it allows for a higher efficiency, a higher mobility of carriers, and so forth, higher electric fields present in stronger electric fields present in the device. The issue with that is that traditionally what you would use in the processing world would be the silicon, but as you can see to the right, there's solutions such as silicon carbide, which is a combination of silicon and carbide, to enhance the band gap and while maintaining the mobility of the carriers. Another example is gallium nitride versus gallium arsenide. Gallium arsenide is also a high band gap material, usually above 1.4 electron volts that are required to move from the valence to the conduction band. That is called a relatively high band gap semiconductor. And an initial example of that was gallium arsenide. Gallium arsenide has been in use since the 60s and maybe even beforehand, but since the 60s intensively in the RF world. It is nowadays you can reach operating frequencies in Fmax and FT. Fmax is maximum current gain, FT is unilateral gain, voltage gain. You can reach frequencies of up to 1 terahertz. So you can have an RF gain of up to 1 terahertz. However, the mobility is high, meaning that why you reach such high frequencies is because of the high mobility, but the applied voltage is low, meaning that at those high frequencies you can generate power, but the power will be lower as compared to a GaN device. A GaN device will not be able to reach the frequencies at 1 terahertz, may operate only till 200 gigahertz, but will give you an output power of 10 times that of gallium arsenide. And so forth. Usually it's a battle between the technologies. Nowadays, I think GaN and GaAs are still Ziege, GaN, and GaAs are what are mostly used in the world of amplifier design, power devices. GaN inhibits this world between 0 to 200 gigahertz in this area where the power density is the highest. From 200 gigahertz to around 400 gigahertz, I would say Ziege is quite advancing in that aspect, that you can have integrity with also combining a Ziege node with a silicon node, so that you can have not just the RF amplification part in one chip, but you can have also other components such as a local oscillator, a VCO, a PLL loop, or whatever you require to form a system inside the one chip only, and not just have these power bars as we saw, just the power bars that parallelize, so have a complete system. And beyond that, gallium arsenide is still mainly used for low noise amplification, and occasionally for transmitters that operate above 400 gigahertz. Why the wider band gap? Because it has a higher breakdown voltage. As we said, you can apply a higher voltage to have a higher output power. It has a better heat transfer. Silicon carbide has a heat transfer which is similar to copper, but allows for a higher breakdown voltage and it keeps the same carrier mobility. What does that mean? It reaches the same Fmax and Ft of silicon, whilst able to carry more voltage, which means that it is able to generate more output power. There's a similar cutoff frequencies. Similar can be said for GaN versus GaAs. That GaN allows for a higher band gap, higher voltage applicable to GaN, and thus also a higher output power due to the carrier density as well. In this regard, an example of a GaN gallium nitride HEMTs are, for example, an example of such a device, and the silicon carbide MESFETs are an example of a device for silicon carbide. Just examples of how the world has moved on from operating with one material, but combining two materials in order to form a heterostructure which is with a wider band gap, so that you can apply a higher voltage and still retain a higher carrier mobility and carrier concentration as well. The higher band gap allows for then substrates which are optically transparent, as can be seen in the example here. It's just to get a feeling about how these kind of wafers look like and in the forms and shapes they come in. Usually what the issue is with these substrates with higher band gap is that they also, due to the fact that they haven't been handled well, they haven't been developed as silicon has been developed in the industry, being pushed by many corporations with regard to applications in computers and phones and whatever. These technologies still are in the level of development, semi-industrial application, but also development, still in research. Thus, the wafers are occasionally quite brittle. The physical properties of them are occasionally not as ideal in handling the wafers, in dicing them, in packaging them, and so forth. Thus, the packaging, the dicing, the handling of these wafers, the processing of these wafers is far more involved than what is in the silicon world, just because of the fact that silicon had so many years and so much push in money and interest to develop and to standardize the process. Additionally, what is the benefit of these high bandgap materials is the polarization. They both enable spontaneous and piezoelectric polarization. The piezoelectric polarization, when applying a voltage, the shifting of the polarization levels, which can be used for generating this 2-DEG layer, this two-dimensional electron gas layer. So basically, due to polarized doping, with no actual concrete doping inside, rather just the aligning of these respective layers, growing of these respective layers with MOCVD, with molecular epitaxy processes. You can grow these layers on top of each other, which then, due to spontaneous and piezoelectric polarization, generate an electric carrier, so like a channel in between that allows the transfer of electrons, that allows the generation of carriers and electron holes, and thus the movement of the current. Comparison of GaN and GaAs, as we said. Why GaN? GaN is a higher bandgap material. It allows a higher breakdown voltage. Applying more voltage versus applying a lower voltage, even though the carrier mobility of GaAs is far higher than the carrier mobility of GaN, still, these properties are the carrier mobility and the band gap and the crystal structure and all that are intrinsic properties of the material. These will then we can see the output is that in comparison the GaN, which is in red depicted, produces a far higher drain source current than what the GaAs, which is in green, depicted. I think the plot here is a bit also not always the case is like that. If moving to the higher frequencies, you can see that there's an opposite. Once gallium arsenide starts to once GAN reaches its FT. But still, the what this plot tries to make apparent is that the higher band gap, higher voltage, thus higher output power for a specific frequency. If we move from 100 gigahertz to 1 terahertz, this will be the opposite because GAN cannot reach 1 terahertz due to the reduced mobility of the carriers. Yes, power semiconductor devices require that other semiconductors require semiconductor properties that operate at high frequency. Silicon is a good reference because silicon was developed over a large time, and then I think the endeavors with silicon carbide and so forth aided the application of silicon still in the large bandgap world and in the application via silicon carbide for devices that have a lot of output power until 4 gigahertz or so can be used, and the wide band gap, as I said, usually it's taken at 1.4 electron volts, but usually here it is depicted as 2 electron volts is taken as devices for a wide band gap. I think what we will do is we'll take a 10-minute break, and then we'll continue with the rest part. Yeah, I'll stop the recording now, and then I'll upload a second part of the recording for later. If you have any questions, please do state them.